All right, so what should we start with today? I mean, we can do 6 part B because it was mentioned, but we can do other ones if people would rather see other ones.
Sorry, since I just popped in, are we talking about qual 4?
Yes, I believe so.
Okay.
So one thing that I should say about qual 4 is that if you click on the website, the overleaf page for solutions, right, and you go on the left and you click Mock Qual 4, and then you click recompile, it'll recompile the Mock Qual 4 document. And I added a hint for all of the problems that didn't already have a hint. Okay. So the problems that already had a hint, those were written as they appeared in past quals or past finals or whatever. And then I added hints to the ones that didn't already have hints.
Yeah, I think I'd also like to see 6 if we're putting in recommendations.
Okay, sure, let's go ahead and start with 6.
I like 8. I like 6 and 8. There's a lead route for you, Katie.
So 6 and 8. Right.
Oh, and 7, because there's a partition of unity. So anytime those are there, I need to work on those better.
7.
I will also throw my hat in for 3B.
Okay. 3B. Okay. I think 3B gave me the most trouble when I was doing some of these problems this weekend, so that makes sense. Okay. How was 1 for people?
Okay, did we talk about 1? Is that the one? I can't remember. No. Yeah, I think we need. Oh yeah, we didn't get the countable dim. Please 1 as well. I think
Please
we're-
1. Okay.
Yeah. Okay.
All right. Okay, I feel like that's a fair spread of these, right? Hopefully 9, like the hint made sense, use the regular level set theorem for part A, and then part B, you graph it, and you're like, wait a minute, locally Euclidean sets don't look like coding points. But then good, right? Don't look like double points. So, okay, cool. Okay, so I'm gonna just say some words about these. Maybe we'll just go in the order that I wrote them here. I'll just assume that the ones people want to talk about first. Okay, and okay, so we got a dog this weekend, so you might hear some dog noises in the background.
Yay!
Okay.
Does your cat like him?
She has been hiding in the closet since this weekend.
Oh.
But this dog has been so good. The first time that he barked at the cat was today. The entire rest of the time he's just been like down, just like wanting to talk to the cat, but like looking at us, and we're like, no, leave it. And he's like, okay, I'll not look at the kid. Yeah, he's a good dog.
Oh, okay.
Okay, so let's go ahead and talk about number 6. Okay, so let G be a finite abelian group. So part A says give an example of an arcwise connected space with base point x comma x naught, such that this thing is such that the fundamental group is isomorphic to that group. So I give a hint which points you to exercises to know B1, right? Which states that the fundamental group of the product of 2 spaces is isomorphic to the abelian product of the fundamental group of the 2 pieces, right? Okay, and so this was exercises to know. B1. And so you're supposed to, so maybe I'll give a sketch of the proof instead of the full proof, right? So use this fact together with a classification theorem for finite abelian groups. There are several of them. You can use whichever one you'd like. The one that comes to my mind is that every finite abelian group can be written as the direct sum I equals 1 to n of z mod, let's do pi z for some collection of primes pi. And so if you've taken like an undergraduate course in group theory, or the group theory course here, then you're expected to know this. And if you haven't, then here's a fact that you should just use in this class, because this is not a group theory class.
Yeah. Well, they're not necessarily primes, they're powers of primes, right?
Yes. You're correct.
Not that it really matters for this problem.
Yeah.
I think you can just say it's decomposes as direct sum of cyclic groups.
Yeah. There we go. Some collection of integers and I doesn't change that thing. Yeah. This is good enough, especially for Verducci and Schultz, because they don't like talking about it. No, they like, or at least Schultz is fine talking about group theory, but Verducci is the only professor that I know that wears that t-shirt that says another day has gone by and I still haven't used algebra, which is just hilarious because, you know, when other people wear that shirt, they mean high school algebra, but when he wears that shirt, right, he reads, you know, ring theory. That's awesome. Anyway, okay, so, and then the third thing that you know, and this is actually something that we talked about last Thursday, is that given an integer n, identifying n pieces of the boundary of a disk, e.g. right, if you identify these four, and I should use different colors because I have access to infinite colors on the computer, so I should at least use some of them, right? That I think the colors actually just made that drawing worse. Let's just not do that. Okay. E.g. for n equals 4, this gives a space with fundamental group isomorphic to z mod n z, right? So you just take the direct sum of as many of these things as you need, and then you get whatever space with whatever finite abelian fundamental group you need. Okay. There is a different version of this question, although it's a much older version of this question that removes the finite condition, right? That says construct a space that has any abelian group. But if you remove the word finite, then you just add on like a bunch of copies of Z to this theorem, which are just circles, right? And that's how you get this. So really, we are just getting a bunch of circles crossed with a bunch of quotients of a disk, right? And that's what our space is gonna look like in general. So
I had a question about like that first, what is it? It's the exercise to know B1 and kind of like similar things. So if you have an infinite like Cartesian product of spaces, does that still apply?
Oh, that is a great question.
It can still be countable, like if that helps at all. I don't need it to be like arbitrarily infinite.
I don't think so. Because things break when you get infinite dimensions. So like the thing that I'm thinking of is some sort of pathological loop that you define in your space, which somehow just like in every dimension, it goes out to one and then back, right? And then if you try to take in just like normal, and I just say normal infinite Euclidean space, as if such a thing is normal, that is certainly right, like not a very, or maybe it is normal in the topological sense of normal, but right, all of your open sets that you would try to put around that set to like find, you know, like nice neighborhoods to like look at like local path connectedness only have a finite number of are restricted in all but a finite number. Are restricted in a finite number of dimensions and not restricted in the rest of the dimensions. So just in order to cover like the beginning of this path, you would need like an infinite collection of open sets. And I feel like that might cause problems with this identification with the paths in the fundamental group with the topological space. Yeah. So I don't know if that's a very good reason, but my intuition says that this probably works for infinite dimension. But if it does work for infinite dimension, it would be one of those things where I'd go like, okay, sure, that might as well be true. Okay, cool. Okay, and then for part B is actually easier than part A. I hope that answered your question, Ken. So the Cipher-Van Kampen theorem this states that the fundamental group of X, what is my rating, is isomorphic to the fundamental group of U, free product the fundamental group of V, modded out by the least normal subgroup generated by I1 of generator times I2 inverse of generator such that generator is in the fundamental group of the intersection or something. Sorry, let me rewrite that so that way this is less squished, is in the fundamental group of the intersection, right? Something like this, right? But by assumption, right, this intersection is simply connected. So all of these phi's are trivial. And if I take the image of a trivial thing times the inverse of the image of the trivial thing, I get a trivial thing. So this is just the free product of the fundamental group of V and the fundamental group of U, right? So if either of these are non-trivial, then I have a free product between two non-trivial groups, which is never an abelian group. That's part of the definition of a free product, right? In a free product, none of your elements from the first group commute with elements in the second group, right? So the Cipher-Van Kampen theorem says that if this is abelian, then this free product has to have that one of these two things are trivial and that the other one is abelian. Or if one of these is trivial and the other one's abelian, then going in the other direction inside from the mechanical theorem tells you that the fundamental group of X is abelian. Right? Yeah, so the key takeaway, right? If G1 is in capital G1, G2 is in capital G2, neither are the identity, then G1, how do I want to, G1, G2 is not equal to G2, G1 in the free product of these two groups. That's the key takeaway, right? And so, yeah, or maybe the key takeaway is that this least normal subgroup is trivial when it's generated by the trivial group. Maybe that's the key takeaway. I don't know. One of those two things is the key takeaway. But in true Schultz fashion, you know a theorem, you say one thing about a theorem, then you get the result. Cool. Questions, comments, concerns?
Yeah, so this was pretty much my idea too, but so when you say that elements, like if you have a free product of A and B, then none of, like by definition, none of the elements of A commute with any of the elements of B. So there you're using part of the definition that says that the free product has the relations on the free product are just the relations of A and the relations of B together.
Exactly.
There's no new relations. So I was wondering what would happen if you had like a free product of A with itself. Then do we like we still count the generators twice, basically, right? Like even though they're the same group, we say
Yeah, so the free product of a group with itself is just that group.
Okay, so it is.
Oh no, wait, is that true?
I think
No,
like
no,
the
it's not
free
true.
product of
It's
Z
not
with
true.
itself is
It's not Z.
Z2. Yeah.
It's also not Z2.
Oh,
The
right.
free
It's the
product of
free group on
Yeah.
two generators. Yeah.
Yeah, exactly. It's the free group on two generators, right? Sorry, I can't believe that I almost said a lie, right? But yeah, if you take the free product of a group with itself, the thing that I like to think about it is that I'm going to color one group red, and I'm going to color the other group blue, and then I'm going to alternate between listing red and blue elements in my word representation, and I'm only allowed to do relations on elements that are the same color, right? So if I have two blue elements next to each other, I can like do group relations to those, but a red element next to a blue element, they don't do anything.
Okay.
Or you write one in regular text and the other one in italics, and it's the same idea. So that way I'm not discriminating against people who are colorblind. Okay. All right. Any other questions, comments, or concerns? Okay. Let's talk about 8 then.
Oh wait, here, sorry, while we're on this, I remember there was a previous problem that Anthony presented that had to do with, I guess it was in part A. Like, could you quickly go over, there was like a covering map.
Two-sheeted covering map and odd fundamental group. Anthony, like we had a 3-point Mobius strip, and
Yeah,
Jacob's like, yeah, identify. And I'm like, wait, how do you actually do that?
Yeah, if you could go over that again, that would be really great.
Yeah, so it's this same, so you take a disk, right, filled in disk. And then you take, say, like if we wanted to do this in the complex numbers, you take the 3 roots of unity, right? And then you identify just the boundary going say, counterclockwise of these three pieces of the boundary, right? So you have this identification of points on the boundary, and the points in the center of the disk are only identified with themselves, right? So this identification forms a quotient space, right? You try to glue these three things together, right? You don't get a manifold, right? This is not a manifold, right? There are rules for cutting and pasting constructions that give you manifolds. And one of those rules is that, or basically the only rule is that edges are only allowed to be identified in pairs. And if you do that, then you get a manifold. Here, my edges are not identified in pairs, so I don't get a manifold. And once you make this construction, the fundamental group of this space is the group with three elements.
So is there like, because I understand the one for RP2, like using
Mhm.
Seaford and Campen, but is
Mhm.
there a nice proof for this, like in general?
It's also cipher bandcamp. It's the exact same proof. It's just that on the step where you get that relationship where the generator for the intersection annulus maps to, right, gets mapped to two of the generators for the Mobius band, right? Here, if you take a single loop around, I'm going to imagine an annulus in here without drawing it. But if you take a single loop around this thing, you get three of these red pieces.
Yeah, I think I'm fine
And
with
that gives you the
part.
3Z
I think
generator.
the part that bothers me is in the RP2 case, like you know that the fundamental group of the Mobius band is S1, which
Mhm.
I can sort of see.
Yeah.
But for like the 3 case, I can't see that, like why the fundamental group of that like new Mobius band.
Yeah, so if I take this thing, the idea is that even though all of these things are identified, I can still take a straight line homotopy, which deformation retracts the entire space down to that center circle.
I believe you, but I just like I don't know. I have such a hard time like seeing it, but just like all the identified points would just like homotopy together, I guess. Okay.
Yeah, so this is not a, okay, so when you normally do a homotope of the annulus, right, the outside boundary of the annulus, when that homotopes down, you get that every point on the outside boundary of the annulus goes to 1 point on the inside boundary of the annulus, right? There's a bijective. Here, it's a 3-2-1 map. I know that I drew this as a straight line, but actually there's like some folding that happens as you go down. And so you get that this point and this point and this point are all going to map to the same point on the inside circle, right? But like imagine like one of those like telescope, like one of those telephoto lenses that like shrinks as you like, you know, like there's going to be like some threefold folding down as you do this homotopy to the center. But
like you wouldn't only get like a third of that inner circle. You actually would get the whole circle.
Yeah. Or maybe this is better, homotope out this way instead.
Yeah, I think that makes, does that make more sense? I think that makes more sense.
And then you just get a circle with these 3 points, with these 3 things identified. But then when you just do this on a circle, right, you just get a single circle. Right? These are the same. And you can even just think about doing like one of these edges at a time, right? Like you fold this bottom edge up, right? And you're like, okay, this point goes here, right? Because the bottom of this has to go to the bottom of this, and this point is the top, so it goes here. Okay, so you send this point here and you send this point here. And then what you get is that the top point does this, right? So I guess that if I mark this one, that one went there, and this one on the right stayed the same. And then I do the same thing, right? Like you think about making this identification folding over the circle, and or do an in-between step here. I don't know, there are lots of ways that I could do this. Do an in-between step and just identify all of the vertices together first. Right. And then this circle and this circle and this circle all get identified to each other. Right. And now you can just imagine just picking up one of these loops and placing it on top of the other loop, and then taking another one of these loops and placing it on top of the loop. Right. Right. You just like imagine like 3 pieces of string that make a rose, and you pick up one of these pieces of string in real life and you just set it on top of one of the other strings, and then you just make that identification, and then you just circle it. Right. Yeah, this is probably a better way to do it, to go to the inside circle.
So you're basically bringing like all those 3 points just to the center, and then
Yeah,
folding.
yeah, since all 3 of these points are identified with the same point, right? They are all the base point of one of these edges. So they're all the same since all the edges are identified. So
Right.
now I'm just drawing them as one point because they're supposed to be one point, and then
I guess, like, how do you convince yourself that this is all continuous? Like, there's no,
yeah, so I know that I'm describing these as like a continuous motion in R3 of like picking them up and placing them down. But this is not at this point, this is not a deformation retraction anymore, right? The deformation retraction happened here. Right? Okay. So now I don't need a continuous motion all the way through. I'm just identifying edges and doing this thing under a quotient map. Right. So like this point has a neighborhood around it, and this point also has a neighborhood around it. This point also has a neighborhood around it. So that way under the quotient map, they all go to this point in this neighborhood around it. Right. And the only weird thing that happens is at this point, right, I have like this 6-fold neighborhood, and here I have a 2-fold neighborhood, but that's because like these 3 edges all get identified to the same side, right? But this is just like a normal quotient map construction, right? So I don't need like a continuous motion through space like in a homotopy, right? I just need like a domain and a codomain, right?
I guess, like, so the very first thing you did with like the red circle or the red weird identified circle and like the homotopy, that's all you would need though, right? In order to say that the fundamental group of that weird annulus, the Mobius annulus, I guess, is isomorphic to the circle.
Yeah, but when you draw it this way, this here, that's the generator for Z. Because that goes once around the circle. It doesn't look like it goes once around the circle, but it does hit every point in this space once and only once, except for the starting point. Right?
Yeah, I think that part makes sense to me. But yeah, okay. But yeah, thank you. I think that helps.
Okay. Where something question. Right. Okay. So for question A, or for not question A, question 8, part A. So it looks like there's a lot of things that we have to prove, right? That it has to be connected, it has to be open, it has to be a subgroup, and that it's diffeomorphic to all of the other things. But of those 4 adjectives, maybe being diffeomorphic to the other things, right? That's a long adjective, but it's an adjective. Okay. We get 2 of those things for free, right? So if we just let GE be the connected component containing the identity element E, note GE is open because components are open and closed. Okay, that's the definition of a component. Okay. Or it's a definition of a component. Right, the connected components are exactly clopin sets of your set. Okay. So if I just start with the connected component, well, connected components are connected and connected components are open. So I get those first two adjectives for free. So I want to show that this is a subgroup of G. And the way that I'm going to show that, right, is, so let's recall some basic theory, right? GE is a subgroup of G if and only if GH is in GE for all G comma H in GE, and G inverse is in GE for all G in GE. Well, it turns out that the multiplication map is smooth and the inversion map is smooth. So we're going to use these two facts to get us the thing that we would like, right? So in particular, we're going to note that GE cross GE is connected, right? Because the product of two connected sets is connected. This is, I think, on exercises to know. It might not be on exercises to know. Maybe I'm lying. Is this on exercises to know? Da, da, da. Yeah, question 10 on part A of exercises to know. Cool. Okay. The multiplication map which I'm just going to denote as mu, which goes from G cross G into G, is smooth, which implies that mu is continuous, which means that the image of GE cross GE is connected. Right? But every connected set in a topological space is contained in a connected component. Right? So this means that mu of GE cross GE is contained in a connected and it's in fact it's contained in a unique connected component. And since the identity element is in the image of GE cross GE, right? Because the identity times the identity is the identity, right? I get that the image of GE cross GE is contained in GE. But what does this mean? I.e., for all G cross H in GE cross GE, mu of G comma H is in GE, but this is exactly the same as saying that G times H is in GE. So what this is, what we've just shown, is we've just shown the first condition, right? Because I started with two arbitrary elements in GE, which I just represented by one ordered pair, the first element's in GE and the second order element's in GE, and I showed that their product is in GE. a similar argument with the inversion map. All right, this is the map which sends G to G by sending an element to its inverse, shows that if G is in GE, then G inverse is in GE. Same idea, right? G is connected, so the image has to be connected, so it's contained in a component, but it contains the identity because the inverse of the identity is the identity, so it must be in GE. So therefore, right, the inverse of any element is. Okay, so we have shown that this is a connected open subgroup of G. Now we have one line to show that it's the only open connected subgroup of G, right? Any other open connected subgroup of G must contain the identity E. Right. An open connected set is a component, right? But only GE contains E since components are disjoint. Right. Right. The subgroup has to be the one that contains the identity, because every subgroup contains the identity element. Right. Open connected sets are components. Right. And so in order to be an open connected subgroup, that exactly describes the connected component containing the identity. Right. Of which there's a unique one, like I said, because connected components are disjunct. So one of them contains the identity and the other ones don't contain the identity. Turns out they're conjugate of the ones that contain the identity. But whatever. Okay, cool. Then the last part of this question says that every connected component of G is diffeomorphic to GE. Okay, so we're gonna let's call G0 be some other connected component. Let G in G0 be an arbitrary element. Then the left multiplication map, which sends G to G by sending H to G times H, right, is a smooth map and we're going to use the image of a connected set as connected argument, right? Right. So LG of GE, right? This is a connected subset of G naught, right? And it's an open subset of G. So LG of GE is a component of G contained in G naught, which is a component. So LG of GE is exactly equal to G naught. And maybe up here, instead of saying that this was a smooth map, I should have said this is a diffeomorphism, right? And so this is a so this is the restriction of a diffeomorphism to an open set, which is again a diffeomorphism, because I just showed that it is, right? Surjective. And the restriction of a bijective map is an injective map, certainly, right? Thus, LG restricted to GE, GE to G naught is a diffeom. You might want to, maybe if I was being more proper here, I would say a couple more words about why this is a diffeomorphism, but the restriction of a smooth map to an open set is still smooth, right? The restriction of a bijective map to a subset is always an injective map, right? Then you just have to figure out what the appropriate restriction of the codomain is to get back your surjective B. Right. Or you could just say that this is a smooth bijection, and alternatively show that LG inverse, which is the same as LG inverse, which doesn't sound like I said anything, right? If you restrict either of these to G0, right, you get a map from G0 to GE, right? Which is also a smooth bijection, right? By the same argument as above, right? So if you don't like, right, that the restriction is, or right, like if you don't like this restriction argument, you can do the similar thing here, but we're just using the fact that these components are open and that the image of an open set under a diffeomorphism is open. Are there questions here? Judging by your faces, I don't know if people are convinced.
Yeah, so I don't know, this may be a dumb question, but so you said that because GE is a connected component, therefore it's open. So do we know that there's a finite number of connected components on a Lie group, or do we get this from somewhere else that it's open?
So a connected component is, one way to define it is it's the largest connected set containing a point, right? So one way to, like, so if you define it this way, right, it's a connected set in your space, right? But if you take that set and you union any other disjoint set, open set, right, that has to be a disconnected separation, right? So using this idea, you can show that a connected component has to be open and closed.
Yes, if there's a finite number of them. Like, for example, like in the rational numbers, then the connected components would just be the singletons.
Mm. Oh, okay. Is there more work that I have to do to show that this is open? No.
Yeah, I think there's definitely a countable number of them at least.
Yeah, okay. I think that you can get around this because Lie groups are manifolds, right? And so even if you have like uncountably infinite disjoint union of a bunch of stuff, right? I still think that this is going to be fine because locally you just look like Euclidean space.
Right. So it's locally path connected. Therefore, the
Yeah.
path components are the same as the components which are open. Okay.
Right.
Okay.
Yeah. Although I guess in the rationals, hold on. Yeah, because if I just take the rationals with the subspace topology, then their components are the singletons, but those components are not open. Yeah. Okay. Yeah, the fact that this is open probably comes from the fact that like the inversion map as a diffeomorphism isn't open. No, that the multiplication map is open, right? So for any element in your group, right, you take an open set around it and an open set around the identity, and then the product of those two open sets is still open and it's around whatever element you wanted. And that shows that between every point, there's an open set, but I don't know, maybe something like this. No, in order to do that, I'd have to assume. Oh well. No, okay, once you show that this is a subgroup, then you get that this is an open subset. But did I use that this was, and showing that this was a subgroup did not require to show that this was open. I just needed that the image of connected set was connected, right? And then you use, yeah, so if you really want to formalize this, you could use this left multiplication map LG to say for any arbitrary element in your space, right? Take an open set around the identity, and you can show that that's contained in your component. And then you map that open subset around any point that you would like, and that's still inside of your subset because I'm just multiplying the identity by something in my subgroup, so I'm still in my subgroup. So okay. Yeah, that's an interesting question. There might be something more than I might have to look back at this question this week and maybe write a better proof than what I presented here, just to make sure that I cross the I's and dot the T's. Okay, but moving on because it's already 9:30 and we've only gone through 2 of these problems so far. So the idea here. So you're gonna let V be equal to U intersect this component that we just defined. Right. And you're gonna define a function G, which maps G cross G into G via G of, let's not call this G. I'm just going to call it G as the name of the function. Let's call this phi instead. Phi of these two elements, G comma H, is equal to the product of G times the inversion of H. Right. Yeah. Or maybe instead of taking this as V, you then let, oh boy. Then you consider the pre-image of your open set U. This is an open subset of G cross G. Right. And you, I think it suffices here to then just take the identity and take two basic open sets, B1 cross B2 is going to be contained in this, because the identity is certainly going to be contained in this. And then you let V be equal to B1 intersect B2. I believe, if memory serves, that this is how this problem shakes. Yeah, I think I have the solution, a nice solution to this problem written somewhere. Or maybe I get that the identity comma the identity is contained in B1 cross B2. Yeah, that's more appropriate because the domain here is G cross G. But then this construction tells you, okay, if I have an element G in B1 and an element H in B2, then because these two elements are, yeah, then by the construction here, right, yeah, this is it. If G comma H are in V, then G is in B1 and H is in B2. So G comma H is in B1 cross B2, which is in phi inverse of U, which implies that phi of G comma H is in U, but this is exactly the same by my definition of phi as saying that G times H inverse is in U. Yep. Okay. So yeah, a lot of the Lie group questions that Wilhelm likes to ask are either questions which are like, hey, there exists a diffeomorphism from any element to any other element via the left multiplication map, right? That's like half of a lot of the problems that Wilhelm likes to ask about Lie groups. And then the other half of problems that Wilhelm likes to ask about Lie groups are problems that you can figure out just by knowing that the multiplication map and the inversion map are smooth functions. In fact, the inversion map is a self-diffeomorphism.
Jacob, can you say that last part? You said the other questions, you kind of cut out for a second. You said the other questions he likes
sure.
to ask for what?
Yeah, the other questions that he likes to ask are just questions that use these two facts, right?
Mm.
That multiplication is a smooth function, and that taking an element and spitting out its inverse is also a smooth map. In fact, this one, it's even better. This one's a diffeom. That's because it's its own inverse function, right? And every element has a unique inverse, so you know that it's bijection, right? All this nice stuff. So, yeah. And so this is one of these types of problems that Wilhelm likes to ask about Lie groups that really just boils down to the definition of a Lie group, right? Do you know that multiplication and inversion are smooth functions? And then a lot of this stuff that like, right? And this problem B kind of speaks to that because it's asking about something about the topology of the Lie group, and that it's asking about neighborhoods. That satisfies a certain group structure, right? Right. And so in order to reconcile that, you have to use the fact that in a Lie group, the group structure and the topological structure are nicely connected via these two functions, multiplication and inversion. I think that you can cheekily define a Lie group by only saying that one function is smooth. Instead of just multiplication and inversion, I think that you can just define this function phi that I defined down here if you wanted. Right? I think that you can say if this function is smooth, then you get a Lie group, but that's because you can just always take the first component to be the identity element, just restrict to the identity element, and you get that the inversion map is this other stuff. Okay, cool. All right, gonna move on to 7. Okay. How do I do 7? Right. So it says that you'll receive 0 points for this problem if you cite the Whitney embedding theorem. But that's because we're basically proving the Whitney embedding theorem. So you're not allowed to cite things to prove. Okay. Okay, so let's do the proof. So this is number 7. So let's let capital M be a compact little m dimensional manifold. We're gonna build a partition of unity, right? We're gonna let C alpha and alpha, or phi alpha such that alpha is A, be a covering of regular coordinate balls. And after last time, I actually looked up in Lie what the definition of a regular coordinate ball was, and I found it. And he does actually define what a regular coordinate ball is. If I can remember where he defined it. Somewhere when he was defining a bunch of these terms for manifolds, he was defining what all these types of balls mean. And I think that he was defining a regular ball as a ball such that the image of the closed ball. Yeah, he defines a regular coordinate ball on page 15. So I'll write that down. So in case you're curious what a regular coordinate ball is, if there's a smooth coordinate ball, which is bigger than the closure, so that way the map of the closure is exactly the map of the closed smaller radius ball. But Wilhelm just defines it as balls of radius 3 and balls of radius 1 that have the same property, and it's fine because you can just rescale these radii as you like. So I just am going to write IE so that phi alpha of C alpha is equal to the ball of radius 3, 0, or centered at 0, and my manifold is covered in not the pre-images of the balls of radius 3, but the pre-images of the balls of radius 1. Since M is compact, there exists a finite subcover of, and I'm specifically going to take the finite subcover of the balls of radius 1 which still covers M. Say, I'm going to call them CI phi I, such that I goes from 1 to N. Okay, now I'm going to define a collection of bump functions, not bump functions, bump functions. I'm going to use psi I goes from 1 to N. On these charts, CI I, so that phi is equal to 1 on phi inverse 0 and psi I is identically 0 on M set minus CI. Okay, so I'm just constructing a required partition of unity here. Okay, so now we're going to define fi, which is a function from M to R. Oh boy, I think I wrote Rm here. No, yes, Rm by fi of x is equal to psi I of x times phi I of x for x in Ci, and it's 0 for x in M set minus. Okay. Note fi is smooth for every I. Okay. So, are there any questions about the construction so far? We have now constructed a partition of unity on our space. Someone who's more familiar with partition of unity could probably just start off with a partition of unity and then restrict that to a finite partition of unity because M is compact. But when I did this, the only way that made sense to me was to go through the process and construct the partition of unity so that I could see what's going on, right? But, you know, Lee makes a big deal about existence of partitions of unity. So you could skip a lot of this front paragraph and writing your own solution and just say, let C alpha be a partition of unity with these functions fi defined this way, right? And then restrict to a finite subcollection.
Jacob, just a question. Why, again, I don't know these very well, so maybe kind of dumb. Why is fix, why is the first branch 2 copies of psi x? Oh, that's a phi. Okay.
Yeah, that's supposed to be a phi. Yeah, let me.
Okay, all good. All right, thanks.
Yeah. Yeah, this is whatever the identification in Rm is.
Mhm.
And this is smoothly tapering that identification down to 0.
Mhm. Right.
Okay, cool. So now we get to the let's build. So all of this was just the let's construct a partition on the space part. So if you've been zoning out before because you are familiar enough to just say, let this be a partition, and you're going to make your notation for partition of unity, then now's the time that you should start paying attention again. So now we're going to define a function capital F from M into, we are not doing an efficient embedding, everybody. We are not doing an efficient embedding at all. Right? We are going to just choose some, right? This is a compact manifold, right? So we're going to use the fact that it's compact to just multiply the dimension by a lot, and we're going to get really inefficient, right? By, and here's how we're going to go, f of x. So the first mn coordinates are going to be these. So remember that each of these is in Rm, right? So I have an R. So technically I have Rm coordinate, M coordinates, then M coordinates, then M coordinates. So I have n of lists of M coordinates. Okay. And then here I'm just going to take and so the reason that this is gonna be this way is that, okay, so big picture, right? A smooth embedding is a topological embedding, which is a constant rank, right? Right, it's an immersion, right? It's constant rank of rank m, right? It's rank whatever the domain is, right? So the idea here is that since my domain is compact and my codomain is Hausdorff, I just have to show that this is an injection onto its image, right? Because if it's an injection onto its image, then it's a continuous function with a compact domain and a Hausdorff codomain, right? Which is smooth. Therefore, it's going to have a smooth inverse if it also has constant rank, if it's an immersion, right? It'll have continuous inverse, and if it has constant rank by the inverse function theorem or something, right? Maps of constant rank have inverses, right? Our inversions have inverses, right? Our local inverses or something like this, right? So, and I actually wrote down where this proposition is. So note capital F is smooth because each component is smooth. And I wrote down this proposition, but I just told you out loud why this proposition is true, right? By prop 4.22 of Lie, it suffices to show F is an injective immersion. That's because if it's injective and it's an immersion, right? An immersion means that it has a local inverse, but being injective means that it's a bijective function. And so that means that the local inverse is actually just an inverse. So great, we just proved prop 4.22. Cool. Okay, so I have to show that it's injective, and I have to show that it's an immersion. This part is going to be the injective part. And this part is going to be the immersion part. Okay. Just as a big picture thing here. Okay. Okay, so let's do these in turn. F is injective. Let's let P and Q be an element of M, okay, such that F of P is equal to F of Q, right? In particular, the bump function of I at P is equal to the bump function of I at Q. For every one less than or equal to I, which is less than or equal to N. So choose J in 1 up to N so that phi J of P is not 0. Then, since the support of phi J is contained in Cj, both P and Q are in Cj. Thus, f of P equal to f of Q, and P comma Q in Cj, this implies that Fj of P is equal to Fj of Q. Wait a minute. Yeah. Yep. And so then just using the definition of what Fj is, I get that phi Jp is equal to, oh, sorry, there's a typo here. Yeah, I think in order to make this work, instead I want, because of the way that I chose this cover, I can choose so that way, instead of this being equal to 0, I can choose it so that way this is equal to 1, instead of being not equal to 0. That is required. Okay. And I have a typo down here with an extra equal sign that I'm not supposed to have. So let's hit the delete button. Okay, cool. Okay, so let me highlight where I made. So here I fixed a typo, just so that way it's clear where I fixed a typo. Right? And I can choose this J because I chose my cover, my original cover, as the covers from the balls of radius 1. Right? That's what I'm doing. And remember that these bump functions are equal to 1 on the balls of radius 1. And then between the ball of radius 1 and the ball of radius 3, they taper down to 0. And outside the ball of radius 3, the bump function is equal to 0. So that's the fact that I'm using here. I'm saying I chose this partition of unity so that way I could choose the bump function where the bump function is equal to 1 around P and Q. Okay. So then what we get here is that, hey, because phi J of P equals phi JQ equals 1, right? I get that phi J of P is equal to phi J of Q, which implies that P equals Q since phi J is injective.
I'm sorry, Jacob, what does that say above the your implication sign, right where your cursor is? Psi J of P equals.
Right above my equal sign.
Above your little arrow, yeah.
Oh, yeah. I'm just restating this fact up here.
Psi
You can
JP.
see my cursor.
Yeah.
But JP is equal to JQ.
No. Yeah. So second line from the bottom, you have psi JP.
Yeah, so this,
P, all
yeah,
of that.
this
Got it.
tiny bit, right?
Yeah, the tiny bit.
Yeah, I am restating. Okay.
That, okay,
Yeah, I'm just reminding you that this and this imply that both of these are 1.
okay. Oh, these are all equals. Okay, thanks.
Right, yeah. Oh, no, I wanted that to be black. Okay. Yeah, I know that this did not read very well. Try to make it a little bigger, maybe clean it up a little, but okay, cool. Okay, and then just to wrap this one up, to show that phi is an immersion, I need to go faster here. So we're going to let x in M be arbitrary. By construction, there exists one less than j less than n such that x is in the preimage of j of the ball of radius 1 of 0. Then phi j x is equal to 1. So fjx is equal to phi jx. Since phi j is mapped from Cj to B3, 0 is a diffeomorphism, dx phi j is an isomorphism. Then we note dx of capital F is just dx of F1, dx of F2, right? We just write out the components, dx of Fn, dx phi1, dx phi2 dot dot dot, dx phi(n). Oh no, wait, I changed my symbols. These are the wrong Greek letters. Right, I used, oh no, those were the right Greek letters. Never mind. Right, so now all that remains to show this is emergent is that I have to just show that this differential is injective, right? So if u v are in R2, no, Rm, right? Or they're tangent vectors at x. Okay, so I should write that. Such that dx fu is equal to dx fv. Then in particular, dx fj of u is equal to dx fj of v, which implies that u equals v as fj is a diffeo, which implies that dx fj is an isomorphism. Thus, dxf is, that is not dxf. dxf is injective, i.e. f is an immersion. Okay. looking at this now, I actually don't know if I needed the second collection of n coordinates. Might have just been able to use the first n coordinates. I think that the proof would have been the same. But this was the solution that I wrote to prepare for Fred's final when I was studying for his final exam. So I'm like, I know that this solution works because he cleared it. He was like, yes, this works. There we go. Cool. Any questions, comments, or concerns? If I remember this problem correctly, and it could be that I'm not remembering this problem correctly, but I think that this problem has been used before as a qual problem, and not just as a problem that Fred likes to put on finals. Like, I think that if you scroll through part C quals, that this is something that he has once upon a time put on in qual.
Jacob, just to strategize, I was asking Katie, like, would it be that like they're not going to ask the same problem that they did on your 2019 qual on, the 2021, right? They don't do that. But would there be something in like this number 7 that shows how you could break this, right? So something like, what if it wasn't compact? Like, would they take a piece out? Because it's probably hard to write new problems. Yeah. So is there something like they just tweak it a little bit? Or it seems like for the differential topology stuff, these are pretty set, right? To use these theorems, you need to have a bunch of stuff. So would there be like a permutation of a problem, or is it just something else?
So I know that Fred tends to just choose very different problems from qual to qual. And you can just tell that by just like looking at his old quals. But if you look at, say, like last year's qual and last year's final, right, which are both available on the website, you can see that for all of those problems, he took a final exam problem. And then he changed the qual problem by replacing the compact domain with a different compact domain. Right? Like there's one problem that was like, show that there's no diffeomorphism between Sn and an open subset of Rn. And then on the qual, he replaced Sn with Rpn. Right? And it's like, oh, the only thing that you need to know about both of those spaces is that they're compact and n-dimensional. And then the proof is exactly the same. Right? So he's known for doing things like this, but yeah, you're right. I don't know. My opinion is that Schultz tends to ask some pretty similar questions from qual to qual. I don't think, from what I've seen, Wilhelm doesn't. I can't promise that he's not going to this year. Right? He might just be like, last year's qual questions were great. Just give them again. But I would highly doubt that would be something that he would do.
And then Vidusi, they don't look similar at all, so.
Yeah, Vidusi just kind of asks whatever Vidusi thinks good questions are.
Yeah. I think we did, we had a question, but I'll ask you later, because I know everybody has to go about the profinite topology. It's defined so different in different like settings, and stuff.
Okay, so let's see. I did not get to question 3b or 7. I don't know if I should say a couple sentences about these or if we should just wait till next time. Or no, not 3b. We just talked about 3b. Okay, I can say a couple words about question 1.
Yeah.
And if you are looking at the hint that I wrote for question 1, then that's the idea. And maybe I'm being a little laissez-faire by just saying that's the idea. So for number 1, the outline, right, is you let script B1 be a finite cover of balls of radius 1. B2 is a finite cover of balls of radius 1/2. B3 of radius 1/3. And then you go forever, right? Forever. Right. Then you're gonna let C be equal to the union I equals 1 to infinity of the set of all center points of balls in script BI. Right? Okay. Or you can let C1 be the centers of all of the balls in B1, and C2 be the centers of all of the balls in B2, and then capital C is just the union of all of those CIs. Right? This capital C works. Right? C is countable because it's a countable union of finite sets. And then C is dense, right? For all X and X, for all epsilon greater than 0, there exists n in n such that there exists n in n and y in Cn such that the distance between X and Y is less than 1 over n, which is less than epsilon. Right? This is just by construction, right? I can choose there's n and n such that 1 over n is less than epsilon, right? And then because Bn is a cover by balls of radius 1 over n, there exists a center point of one of these balls within radius 1 over n to whichever point, right? You just choose the covering element for that point, and then the center point for whatever that covering ball was. Right? So writing out the details nicely, right, would be nicer, but I'm 5 minutes over, so you got the very rough outline.
Can you scroll back up just for 1 sec?
Yep.
Yeah, perfect.
All right, you're welcome, Jennifer. See you later. All right, I think I'm going to stop the recording now.
Yay, all right, well, thank you so much.